Okay, welcome back everyone. I'm going to kick off this afternoon session with looking at vectorization. Okay, so it's a reminder what we're talking about here. So modern CPUs can typically perform multiple arithmetic operations on each cycle. And one of the ways they do that is to use special instructions called vector instructions, or SIMD, stands for single instruction, multiple data. So there are various different instruction sets that encode vector instructions such as SSE and AVX, and there are other ones for different architectures. So ARM chips, for example, have their own vector instruction set. So typically operate on a vector of data. So this will be 2, 4, or 8 double precision floating points. On AMD Rome, it's 4. Okay, so they are 256-bit vector units. So that's 4 double precisions. So potentially this gives us some speed up for floating point operations, and usually this is based on loops, and normally you find that there are only one loop in a loop nest can be vectorizable, and most compilers will only consider vectorizing the innermost loop in a nest. Okay, so yeah, we're doing the same operations on multiple data items. Okay, so essentially you can see that we have some code that looks like this. Okay, so for adding 2 arrays together to give a third array, then using normal instructions, we would be adding 1 element at a time. Okay, so we would be doing serial. We would need to do 4 elements. We would need 4 separate sequential instructions to do these additions. Okay? But using the vector instructions, we can do 4 of these at a time. Okay, if these are double precision, then we can get let's have a pointer. Okay, then we can have an instruction which encodes for 1 instruction encodes for 4 additions simultaneously, and they get executed all at the same time in the vector unit. Okay. Yep. So Rome processor is AVX 256. So that will do you either 4 double precision or 8 single precision operations. So when you turn on enough optimization in your compiler, it will generally try to use vector instructions, but that relies on the code being vectorizable or in a form that the compiler can convert to being vectorizable. So some compilers are better than this than others, but there are some general guidelines about what's likely to work and what's not. So when's the compiler likely to vectorize your code for you? So what can be vectorized? Well, typically only loops, and as I said before, only 1 loop is vectorizable in the nest, and most compilers will only consider the innermost loop. Okay. So how can you tell, okay, whether the compiler's done anything useful for you? Well, you can persuade the compiler to produce an output listing, which may, depending on the compiler, may or may not give you sensible or useful information, or you can look at the assembly code. So you can look for AVX instructions in the assembly code. So instructions using the vector registers, okay, depending on the width of your vector units, and instructions that start with a V on the front. So, so VADs and VADs and VMULs and so on. So what do we need? What are the requirements of our loops in order for vectorization to take place? Well, first one is that the loops must have a determinable trip count at runtime. Okay, so and what does that mean? It means that it must be possible to compute before the loop starts how many loop iterations there are going to be. So it doesn't have to be compile time known, but it has to be computable at runtime. So that tends to rule out most while loops where that information cannot be computed easily at runtime. Okay. For the most part, it must be loops that don't contain any function or subroutine calls unless the call can be inlined by the compiler. Things like mass library functions are usually fine. But that also depends on whether your compiler has a vectorized version of the mass library available. Typically, loops mustn't contain any branches or jumps, though some patterns are okay. So things that are basically just determine whether or not, so tests that just determine or not whether a particular operation takes place and doesn't otherwise jump the control flow anywhere, can maybe okay. So statements like this. Okay, so if AI is not equal to 0, then BI equals CI times AI. So that it may be possible to still vectorize that. Okay, it's not necessarily terribly efficient, but it can be done. And then for vectorization to be effective, well, we either need long loops, okay, or if they're short, then they should be a multiple of the vector length. Okay, because if the compiler is going to use vector instructions, that means it's doing a block of with AVEX 256, then that'll be a block of 4 or 8 loop iterations at a time. Okay? So any remainder iterations have to be executed with plain old sequential instructions. So if the loop's very long, then those sequential instructions at the end don't matter very much. Okay, so if the loop length doesn't divide nicely by the vector length, then having a few sequential, if we have a big long loop, thousands of iterations, then having or even hundreds is fine. Then having a few sequential instructions at the end doesn't really matter. Okay, but if the loop is short, then it's only going to work very well if it's actually the loop is a multiple of the vector length. Okay, what else? So loops must have no dependencies between iterations. Reductions are usually okay. So formally, if you have something that's forming a reduction into a scalar inside a loop, then formally that's a dependency. Okay, so because the value on this iteration depends on the value of some in the previous iteration. But compilers can generally recognize, for the most part, that pattern and deal with it. They're not necessarily so good at dealing with induction variables. So this is where we have a variable with a constant increment every loop iteration. So they may not deal with that case very well. Again, that's formally a dependency. There's typically an easy the value of index is just some linear function of the loop iterator value, so it can be computed directly rather than incremented. but sometimes you might need to implement that by hand rather than relying on the compiler to do it. Okay. It's often helpful to use the restrict keyword in C to tell the compiler that you're not doing anything nasty with pointers. But in the end, you may need to tell the compiler if it can't work out for itself. You may need via directives or possibly compiler flags, usually directives, to tell the compiler that it is safe to vectorize because the loop iterations are in fact independent. And then also have to care about the alignment to data. So the vectorized loads and stores are most effective if they are operating on 32-byte aligned addresses. So you either like to let the compiler do its job, or if the compiler can't work out, you need to tell the compiler what the alignment is. We'll come back and talk more about alignment later on. The usual problem is that if you pass something through the argument list to a function, then the compiler has no idea, cannot tell what the alignment of your array, say, might be, because it doesn't know what, you could pass any old, the thing that you pass at the start might be any old element of the array, so it doesn't know. And again, for the best case is usually if you have unit stride through memory. So you're going, your loop iterations go through arrays one element at a time, and don't jump around. So all in all, that is quite a big list of restrictions on things that will work for vectorizations. Okay. What do you need to do in terms of compiler flags to enable it? So for Cray, C and AMD compilers, you need optimization turned on. It needs to know what hardware it's compiling for you. That's on ARCHER2, that's added automatically. The MArch flag is determined automatically. On other systems, you might have to take some care if you're on systems where login nodes and compute nodes do not have the same chip architecture, then there are cases where you might need to specify MArch specifically for the target architecture on the compute nodes. It's not the case on ARCHER2. The login node chips and the compute node chips are the same, and the compiler picks the right version for you. You can disable vectorization if you want to, and not turn off other optimizations with fno vectorize flag. That can be useful for checking for checking whether your code vectorizes or not. So another way to check, way to see whether vectorization is making any difference is just to basically turn it off and see if it goes any slower. The Cray compiler will provide you with vectorization information with the appropriate flags. Okay, and for other compilers, so for Cray Fortran, for example, the listing flag that you want is -HList equals A. So that gives you an annotated version of the source code telling you what it did. GNU is not so great. There are some flags that you can use, but the output tends to be very long and not very easy to interpret. Okay, yeah. So did my loop get vectorized? Check the compiler output, okay, or read the assembly code. You can also get clues from CrayPat as well. So it's a little bit complicated. But if you turn on the hardware counters for floating point operations, you can see, okay, and you look at the ratio of operations to instructions. So if that's bigger than 1, that means you're using you're using some vector operations. So, and in the ideal case, it should be, if everything's vectorizing properly, then that you could get up to a value of 4 for the ratio of operations. You should be getting 4 operations per instruction, for example. Okay, yeah, and there's a bunch of other stuff that you can try for GNU compilers. Okay, so what happens? What can you do if your code is not vectorizing? If your loops are not vectorizing? So, well, first of all, is it actually, does your loop actually have dependencies or not? Okay, so things like counters say maybe okay, that's maybe handled okay, but either you tell the compiler that it's safe to vectorize. If the loop doesn't have dependencies, but the compiler can't figure that out, then you can tell it that it's okay. Otherwise, you're going to need to rewrite your code without dependencies. Okay? So there's various tricks we can do here. Sometimes promoting loop scalars to vectors can help, and using calculated values based on instead of these induction variables. So instead of having a variable count equals count plus 2 and then using that to index an array, then you might just just replace that with a direct computation based on the loop index. Okay, what else can you do? Okay, try and get if statements out of the inner loop if possible. Okay, so again, you might need some temporary vectors to be able to do that. Okay, sometimes it might be the case where the compiler just decides that it's not worth vectorizing. Okay, and that's maybe in the case where there simply aren't enough instructions in the loop. So perhaps loop unrolling might help. Okay, so yeah, you have loops which mess around with pointers, non-unit strides, so strange memory access patterns, unaligned data accesses, conditionals, data dependencies. So these can all cause problems. Okay, so things like this, okay, where we have indirect addressing. So J is a is read from a value of in an array, and then that's used to index. So that kind of thing causes problems. The compiler cannot easily tell that all the cannot in fact tell at all that the J values are independent, are never equal to each other. So it can't tell there's no dependencies here. So yeah, and using things like using a pointer as the using contents of a pointer as the upper bound for loop and so on. That's also things that are likely to cause problems. Okay, so how do we help the compiler? Okay, so depending on which compiler we're using, we can tell it the loops are independent. So for example, for Clang compiler, so that's the Cray C compiler, say hash pragma Clang loop vectorize enable, okay. Or IVDEP is for Fortran. Tell it that you're not messing with, telling that you're using this correct use of the restrict keyword, okay, which says that no two pointers will ever point to the same thing. Get your arrays aligned to cache line boundaries. Tell the compilers your arrays are aligned if it can't work it out, and try to make loop sizes explicit. Okay, so if the compiler can see, say the compiler can see the loop length, then that can be helpful. Okay, so in this case, okay, we say, okay, let's avoid using, let's explicitly dereference this pointer. Okay, so not have it hanging around inside in the loop bounds, and we can say, okay, pragma, this tells it that these loop iterations really are independent. It's basically telling the compiler that effectively that the no two values of j are the same. So this is safe to vectorize. Okay. Other examples. Okay, so this one doesn't vectorize either because of this dependency here. Okay, we've got x equals x plus something. Okay, something that's not a constant. That's some function of the loop indices. So the compiler cannot tell that, it cannot handle that. It cannot cannot vectorize because the value of x in each iteration depends on the value from the previous one, and there's no way that it can unravel that. So you can do something like, okay, let's expand this is where we can do scalar expansion. So instead of having x as a scalar, we can actually have x as a vector, as an array, okay, and initialize all the values in a separate loop, and then use x of j in here instead, and that should help. Okay, so these are rather old slides. I'm not sure that you would reproduce the performance results necessarily on the latest versions of the compiler, but so this is what the Cray Fortran compiler output looks like. Okay, so if you do -hList equals a, then you get this annotated version of the source code, and then with some markup at the end. So there's a little key which tells you what all these abbreviations mean, but then you also get some annotations. It says, okay, it says a loop line starting at line 16 was not vectorized because a recurrence was found on y at line 20. Okay, so it's basically telling you that there's a dependency in the loop and it can't deal with it. It tells you it did manage to unroll the loop though, and again it says it's also, so it is actually trying to do vectorization on both. The Cray compiler will actually try to do vectorization on outer loops. So this one, it says it's failed on the first one. The inner one was unrolled, but the inner one was not vectorized because it also found it found the recurrence on x here. And then if we do the transformation, sorry, this is a little bit small to see, but if we basically do the transformation, then it says, okay, the loop, and then it tells you that yes, the loops were vectorized. Okay. Getting a data alignment is really helpful for performance. Okay, so for example, if we have the situation where the data that we want to load into the vector register is not aligned with the start of the aligned with the start of the cache line, or not aligned with the with the appropriate place in the cache line, depending on the size of the words and so on. So if we want to, if the first element of our vector is actually the third element of the cache line, for example, then it'll still work, and the compiler will still probably tell you that it's vectorized, but it just won't be very effective. It will basically have to do, if my loop actually starts here, then it'll have to generate some sequential instructions at the beginning, then a bunch of vector instructions, and then some more scalar instructions at the end. So you can end up with with 3 different versions of a loop. So if you are, and also you can end up with different with having to do multiple loads. It might not necessarily be able to load all the data into the vector register at once, etc., etc. So okay, basically, if we can get the data aligned, then we get the minimum number of data loads, and it will still generate 2 versions of a loop, because it might have to have a remainder, but it will typically be more effective. Okay, yep, aligned data is best. Okay, so how do you align your data? Okay, so again, compiler dependent stuff. So you can use special malloc calls. For example, if you're doing dynamically allocated data in C, and tell it there's an extra argument to tell it the alignment that you want. Or there's a line attribute in Fortran. Okay, so for Fortran you can say, okay, please align the array A on a 64-byte boundaries. Again, and then same but different for static declarations. You can't, if you use old school Fortran common blocks, you can't use directives to align data inside a common block, but you can align the start of the common block. But it's then up to you to pad your elements inside the common block to make the components of the common block align. Okay. For derived types, you may need to use the sequence keyword and also manually pad data structures to get the right alignment. Be careful with multidimensional arrays. If you do an MM malloc for each dimension, you should be fine. If you just do a single dimension one, then you can run into problems. If you've got something that's if you've got an array that's effectively 16 times 15, then you can say, okay, well, actually, when I come to this at the inner loop, then it might not be things might not be aligned correctly. So as well as actually aligning data, you also need to tell the compiler that it's aligned. Okay, and there's a number of different ways of doing this. Okay, so specify that you can just say, okay, well, all the data, all my data in the loop is aligned. Okay, or you can say tell it that particular arrays are aligned. Okay, or you can say that you can tell it certain things about values. Okay. Also talk about later. Okay, so there are actually these days vectorization directives as part of the OpenMP standard, which we'll talk about a bit later on. So you can also do that via the OpenMP SIMD directives as well. You can tell it that. So this is telling the compiler that the array A is in fact aligned on a 64-byte boundary. Okay, Fortran, yeah, the way you pass data can affect things because the compiler is basically generating the code based on contiguous data. And again, you might need to tell the compiler that the arrays are aligned. Yeah. So if you have assumed size arrays, then the compiler doesn't know whether these things are contiguous or not. So the compiler will typically generate different versions of the code, but you still need to tell it whether they're aligned. And again, also for assumed shape arrays as well. Okay, yeah, indirect addressing can be, so if I have things where I use indirect addressing arrays, then you need to tell. Okay, so the compiler will do this, but it's compiler can deal with this if you tell it that it's independent, but it's just not very effective. It's basically having to gather the to do a bunch of loads, to gather things together in a contiguous temporary, and then use the temporary. So it tends to increase there's an increased cost. There's some temporary. It can imply some temporary storage, so an extra copy of things. But it will work, but it just won't be particularly effective. Okay, so I mentioned OpenMP. So as of OpenMP 4, which is actually quite a while ago now, it supports SIMD directives. So problem as you've seen is that a lot of these compiler directives are compiler dependent, so porting code becomes a bit of a pain. So OpenMP has a standardized set of these things which you can use. So how does that work? In OpenMP, there is a SIMD directive which says a loop should be vectorized. So this is basically telling it that the loop iterations are independent. So this will cause the execution of the following loop. So this applies to a loop, and it says, okay, this loop will be executed in SIMD chunks. And this does not, however, divide the loop iterations across threads. Okay, so this is in addition to hashpragma OMP4. So it doesn't do this. OMP SIMD on its own does not do threaded parallelization, even though you're sort of telling it the compiler the same thing. But this does not do multi-threading. But you have to combine both together if you want vectorization and multi-threaded execution. Okay, so you just have to be aware that this is not a hint. Okay, you are asserting that the loop iterations are independent. If you get that wrong, then your code may generate incorrect results. Okay, so there are other things you can do. You can say, oh, you can specify a limit on the number of iterations in a SIMD chunk. It will deal with variables, with these induction variables. So you can declare a variable as linear if it's one of these induction variables that is incremented by a constant amount in each loop iteration. So there's a way of telling it about those and dealing with those. We've already seen the alignment, tell us about the alignment. You can also use you can also tell it about private variables. You can also tell it about reductions, and you can also use collapse to get it to vectorize, to unwind multiple loops in a loop nest and vectorize the resulting long loop. There's also a for certain, as long as your function is is a nice function in some sense. Okay, so pure functions in Fortran, for example, you can say declare SIMD. Okay, and that will generate SIMDized versions of functions. So it makes vectorized. It can deal as a way of dealing with function calls inside loops and vectorizing those. And say, yeah, if you want both parallelism and thread parallelism and vectorization, then there are combined loop structures. So you can say hash pragma OMP for SIMD, and then you get both. Okay, so I'm just going to finish up this with a few real examples of. So these are from codes that I've actually been working on relatively recently. So because I just find them quite instructive and show the sort of things that you sort of problems that you might come across. Then in real cases. So first one here. Okay, so basically have a loop. And it has some does some rather messy index calculations, as you can see. But that's not the issue here. This loop doesn't vectorize, and the problem is because of this if test here. Okay, so the compiler isn't able to deal with this. It can't find a transformation where to get rid of this if test. Because it does depend on the if test depends on the loop iterator here. However, okay, it turns out that if you stare hard at it long enough, it means that you will see that this this loop is counting downwards, and it turns out that this branch is taken for everything except the last iteration. Okay. So it turns out there is actually a straightforward transformation here. Okay, I can simply get rid of the if test and do the last iteration as a separate statement afterwards, and this now vectorizes quite happily. So that's a nice, fairly easy case. Where the compiler failed, but you can find an easy solution. Second one is also interesting. So it's actually from the same code. So in this case, so again we've got a loop saying this computes a whole bunch of scalars, and then does some array operations. But here. Okay, so we're writing to the array element IL plus 1, and that depends on the elements IL and IL minus 1. So it's some sort of recurrence relation type thing. And so this dependency here prevents vectorization. And so this. There's not much you can do about that dependency. That's really part of the algorithm. But we might consider that actually what's really the expensive thing in this loop is probably actually the divides and the square roots. Okay, so they're quite expensive operations, and the array accesses and adds and multiplies in here are probably less important. So what we can do with this one is split it in two. Okay, so in order to do that, we need to do a couple of these scalar promotion things. So whereas in the original version, d beta and d alpha, okay, which are used in this final statement here, are scalars. If we promote those to arrays, and then split this loop into two, so that the first loop calculates an array of d betas and d alphas, and then the final loop uses them in the recurrence. Then this we find that at least the first loop will now vectorize. So the loop that contains the expensive operations will now vectorize. The danger of doing this kind of scalar expansion is that if these arrays are large enough so that they don't fit in your level 1 cache, then you will incur some additional costs for that. For this particular code, the length of these loops was not long enough to worry about. It was kind of on the order of 100 or 1,000 or so, and these temporary arrays do fit in L1 cache, so not too much of a problem. If it turned out that you had to deal with cases where this loop was much longer and these temporary arrays would be much bigger, then what you would probably need to do is to block the loop up. Okay, so you maybe say, okay, I'll do 1,000 iterations of this loop, and then 1,000 of this one, and then go back and do the next 1,000 of this, and so on. So Andrew says, yeah, you need to estimate the extra amount of memory. Yeah, so you need to say, okay, how much, depending on the length of these loops, how much extra memory am I going to need, and is that going to fit in my level 1 cache or not? So yeah, you'd need to calculate that and then say, okay, and then if it's bigger than that, then do the blocking thing and to choose your block size so that the temporaries will fit. Yep. And then the third case is kind of a little bit harder to read. Essentially, it's what this is doing is basically doing a series of small matrix vector products and storing the results of that in an array. So it's actually using Fortran intrinsic mapmul to do this, even though it's not really a matrix. It's not actually a matrix multiply. It's only a matrix vector, because the second argument here is it only has one dimension. And so, but it kind of looks sensible, because you've got these matrices are quite small. Okay, the matrix dimensions are typically like small numbers like 1, 2, or 6. But the problem with that is that's the implied loops inside the mapmul call are really too small to benefit from vectorization. So whereas this outer loop, the outer K loop, is this is kind of order of 100 iterations or something like that. So what we can do here, okay, so is to basically what we want to do is basically I want to move this outer loop over K to be innermost, and then if I can get that to vectorize, then that's long enough to actually benefit. So I can do that, but that would give me, because basically IK is just the IK index here is just linear in K here. Okay, that would give me bad stride. Okay, so at the moment this has the accesses into this matrix array here are nice and cache friendly. So if I do it the other way around, then they are less so. So what I ended up doing for this one was essentially you can get rid of the mapmuls. They're not actually helpful. In fact, on some depending on which compiler we're using, then basically just replacing the mapmuls with plain old loops is actually better. The mapmul doesn't help for small. The intrinsic call does not help for small matrix vector products. So if we can basically, if we do that, okay, get rid of the map mulls, replace them with ordinary loops, and then rearrange everything. So rearrange all the loop orders, then it looks like this. And then we also reorder this this three-dimensional array. Okay, so that means that now the innermost loop is the long one, and it's independent, and all these array accesses here are in fact unit stride. So that then works quite nicely. So we now have a performance inner loop that vectorizes well. Okay. Any questions on this one? Especially now, unfortunately, the difference between using loops and array syntax. So for vectorization, no, it's fine. The compiler is just going to translate those things into loops anyway, and then it's able to vectorize them. So typically, no. Okay, it doesn't have array syntax doesn't have too much of an impact on performance. So the thing that is bad is passing non-contiguous subarrays around the place. So if you're picking out non-contiguous subarrays out of multidimensional arrays and passing those around, that tends to be bad because the compiler has to make temporary copies. So there can be a lot of implied copying going on. But just plain old array syntax is fine. One possible downside is handling it with OpenMP. So if you want to do OpenMP parallelization, there is a special directive in OpenMP called workshare, which will parallelize array syntax across threads. But it very often doesn't work very well, and you get better performance by explicitly exposing a loop and using the normal loop directives. Anything else? Okay, in that case, so we've got one more talk to do about memory. So is the calculation of IK not a problem here? No, because it's just a linear function of K. Okay, so that actually turns out that's not a problem. Okay. So I mean, the compiler will figure that out, and it'll essentially just generate. It will be okay. It will just be able to. What compilers usually do in this sort of situation is that the index calculation actually disappears in the optimized code, and you will simply get an increment on the address of the thing that it's being of the array that it's indexing into. Okay, so if you look at the assembly code for this sort of thing, once this has been optimized, you will find that this calculation isn't actually ever really done. Okay, it'll hoist the base value calculation outside of the loop, and then it'll just figure out that it's a single word going from one value of going from matrix the value of the index here is just incrementing. It figures out that the increment is just by 1 every loop iteration. So all you will actually see in the assembly code is an increment to an address, and it'll handle that. The compiler can handle that perfectly okay. Yeah. Yeah, if I'd had the other situation, if I'd done that, if you kind of half did that by hand, by setting the initial value and then sort of and then doing sort of ik equals ik plus 1 inside the loop, then you'd have an induction variable which the compiler may or may not be able to handle with respect to vectorization. But because this is a direct linear calculation on the loop index, it works fine. Okay, so I suggest we take. I need to get a drink, so let's take a short break for a few minutes, and then I'll resume with the next lecture. Okay, let's crack on with the final session then. So we're going to finish up with talking about memory optimizations. Okay, so why? Okay, why is this important? Well, with current hardware, memory access is one of the big, it's the most significant resource impacting program performance. And so, changing the way your memory is laid out and the way your memory is accessed can have a big a big impact on your code performance. The downside is that your memory structures are frequently global to the program, or at least they are used in multiple different program units because your different code sections tend to communicate with each other via these memory structures, and so the programming cost of changing a memory structure can be very high. So, for example, in that last example I showed you about in the vectorization one, where we decided to change the index order of that array, that was actually defined in a structure somewhere, and that affected I think there were more than 100 different places in the code, in the whole code base that needed changing based on that, just to do that one index swap, which is quite a big job, quite a hard thing to get right without screwing it up. So yeah, it's not something that you can typically do easily or lightly. Okay. However, so at best, the compiler is very limited to what it can do with data structures. Okay? So compilers are good at transforming code and reordering instructions, but they are typically pretty limited in their ability to redesign or reorder data structures. So they will hopefully do the best with what you give it, but there's very little that they can do themselves. So changing the idea is that changing the memory structures hopefully allow the compiler to generate better code, as well as potentially improving the locality and making better use of your cache hierarchy. So different types of structure we can think about. So arrays, pointer arrays, records or structures, things like trees and lists, and objects. So arrays are probably one of the commonest data structures in a lot of HPC codes. So they are very handy for representing regular discretizations of of contiguous fields. So we very often end up with three-dimensional arrays. Okay, so typically in either C or Fortran, we can either use you can either use explicit multidimensional arrays, or you can flatten everything and do the index calculations yourself. So way back when, there was certainly some advantage, particularly in C. There was a distinct performance advantage available from writing code like this, where you have one-dimensional arrays with explicit index calculations to treat it as a two- or three-dimensional array. These days, C compilers are typically way better, and doing this kind of thing is absolutely fine. There's really very little need to write this kind of code in C these days. So the address calculations do require something, but if your loop indices and if your array indices are a simple map to your loop indices, then the compiler will typically do a good job. So it does this optimization where effectively the loop index never needs to be actually calculated, and all you see in the assembly code is address increments to move to point to the next element of the array. Okay. But nevertheless, okay, yeah, compilers may do better if it can see the array dimensions at compile time. So we end up with a lot of code. You see an awful lot of codes where you have this idea of looping over array elements is everywhere. So that's essentially nice for the compiler. It's a regular data access pattern. It can handle it and optimize your code. Okay. Important thing to so Andrew says, in Fortran, is there cost to using allocatable arrays rather than arrays using parameters for sizes? Essentially, no. Okay, allocatable arrays are absolutely fine. Okay, there may be some cases where the compiler knows array dimensions. It might do better, but for the most part, it's absolutely fine to use allocatables. We'll talk a little bit more about that later on as well. So the important thing, which I'm sure many of you will already know, is that we want to, for good spatial locality, we want to access neighboring elements of the array on consecutive iterations of the innermost loop. So we want to arrange as far as possible to have stride one access through our arrays. Okay, in order to get good cache use. So unless our loop nest order and array index order match up correctly, then we might not get very good cache behavior. So in simple cases, the compiler may be able to fix that for you by transforming the loops. But in anything other than the simplest cases, it won't. So it is usually incumbent upon us as programmers to get this right. Okay, so sure. So this is okay. To remember that this is the opposite way round, if you like, in C than it is in Fortran. Okay, so if you're unlucky enough to have to swap between the languages, then you need to remember which is which. Okay, so for Fortran, the leftmost array index is contiguous in memory. Okay, so for this example in Fortran, the first version of the loop, so we have I outermost and then J innermost, and I is the leftmost index. This is the bad case, okay, because so J is incremented most rapidly, so we are taking long strides between successive accesses into the array. Okay, but this is the good case. Okay, so I innermost. So in Fortran, we want the innermost loop index to match to the leftmost array indices. And in C, it's the opposite way around. In C, the rightmost index is the one that varies, is the one that is contiguous in memory. So in that case, this is now the bad case in C. Okay, so having J rightmost and I innermost is bad. We want, for good behavior, we want, okay, J rightmost and J innermost. Okay, so this is probably familiar a familiar idea to a lot of you already. Why is this the case? Okay, so to think about what's happening with the caches, remember that when we load data into the cache, we're loading an entire cache block at a time. So that's that's say 64 bytes of contiguous memory. So if these are doubles, then if we're going stride 1 through the array, then we are guaranteed that we take if an array element is not currently in the cache, we have to go and fetch it. Then once we've fetched it, then the rest of the cache block's already there. So it means that the subsequent 7 accesses are already in the level 1 cache. So we will only have, in this case, we only have a cache miss on every 8th iteration of the inner loop. Sorry, this is this case. Okay, in this case we only have a cache miss once every 8. Okay. For this case, if the array is big enough and things don't stay in cache, then we can end up in a situation where we take a cache miss for every single access, because they are subsequent accesses are to different cache blocks. Okay, yeah, dynamic arrays. Okay, it's not always possible or desirable to have fixed array sizes at compile time. So we can do allows both dynamically sized based on subroutine arguments, and also you can do allocatables as well. But the address calculations can still be optimized by the compiler doing common sub-expression elimination, and the size of the slowest moving index is not needed. Okay, and that's why Fortran actually allows you to not specify that in subroutine arguments. So that's why it allows you to do assumed size arrays. Okay. C does require your array dimensions to be known at compile time if we're not doing dynamically allocated memory. You can do some nasty tricks to make the slowest dimension variable with pointers and type defs. So you can do a type def for the innermost. If you want 3-dimensional arrays, you can do like a type def for the 2 inner ones, and then a malloc for the outer one. That'll still work fine. Okay, so we can also have do the full malloc thing. You can do pointer arrays in C. So this is basically, in some sense, it looks like an array, but it's not really. It's actually, it's actually a pointer to an array of pointers to an array of pointers to etc. 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 and eventually pointers to data at the end. Okay, so you can do your classics and nested mallocs where you malloc the point, you declare a pointer to a pointer, put a pointer to pointer to a pointer to a float, and then you malloc the outer one, and then you malloc all the inner ones, etc. 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 Okay, so C kind of cons you into thinking that they're the same thing because you use the same syntax. Okay, that these pointer arrays are really the same as fixed dimensional arrays because the syntax for accessing them is the same. But really, for pointer arrays, is actually pointed. You have to do the pointer dereferencing here. Okay. So the advantage of this X is that you don't have to. Not that everything has to be the same length, but the downside is that potentially you need multiple memory accesses per element access to dereference the pointers. So if as long as you're striding through the innermost one, that's fine. Okay. Because that the innermost index is contiguous, but the other ones could be if you change I, then that basically that could point anywhere and have to go and start from the original pointer and figure out where everything actually points to. Okay, records and structures. So they are. So it's nice programming convenience. So use structs in C or user-defined types in Fortran 90 and later versions of Fortran. So it's possible that if you can store related variables close together in memory, then that might help cache use. But that's only true up to a point, because very often what you have is a structure with a whole bunch of values in it, but a particular individual routines may only access a subset of the values, and so in terms of cache use, if once you're accessing the one value, then you're going to get the surrounding values in memory also loaded into the cache, and unless those are also going to be used in the same routine or in the same loop, then that's basically wasted space in the cache, and you're going to get extra misses. Okay, so when you declare a structure, you're really only specifying what the structure contains, and the compiler is actually choosing the memory layout. So in C, the compiler will usually preserve the order of members, okay, but it will insert padding between them to try and align everything nicely. Okay, so if you have doubles if you have, say, a mixture of ints and doubles, then the doubles have to be aligned on double word boundaries. So it means you will get, if you have an int followed by a double, you may get like an int and then a 4-byte gap and then a double, so that the double is aligned correctly. So that makes your cache, potentially makes your cache utilization worse. So you might want to think about the ordering. So depending on how things are used, but you might want to say, okay, I'm going to have all my ints in the structure together, and then all my doubles together, rather than interleaving them, because then that will make it more compact in memory. Same in Fortran, you can use the sequence keyword to force the deterministic layout to tell the compiler to do exactly what you tell it. Okay. But then we're often faced with this, often faced with choices about layouts. So should you structure your code? So this is the array of structs or struct of arrays argument. Okay, now, suppose I have a particle code. Okay, so I can lay out my data so that I have a structure which represents one particle that maybe has its X, Y, and Z positions and an index and a mass in there. Okay, and then I can declare an array of particles. So the other way to do it around is say, well, actually, okay, I'm going to have a structure that represents all the particles, and that will contain an array of X's, an array of Y's, an array of Z's, and so on. So that's the structure of arrays type layout. Okay. Well, which is best? Well, the answer is, unfortunately, it depends. Okay. So good things about the array of structs idea is it may have good temporal locality. If you're doing a lot of computation on each struct, then if you're loading a struct from memory and doing a lot of computation on it, then typically you're going to be reusing that data quite a lot. But if you don't, if you're basically striding through, if I'm basically striding through this array and I'm only accessing, say, the mass field, then every time I load the mass field, I'm also picking up all the rest of the structure into the cache as well. It's typically not, okay, this doesn't favor vectorization because the things that you are not typically accessing contiguous memory addresses, or you're not accessing contiguous data in a loop. And of course, it's if you're in OO design, of course, it's a very natural thing, but it's a very natural thing to do. It's it's very nice software engineering convenience. On the other hand, if we go down the structure of arrays loop, okay, it might have some better spatial locality, because if we loop through the arrays, then we're going to use all the data on the cache line, but the temporal reuse may be worse. Okay? So it depends on whether which one of these wins out, whether the spatial locality or the temporal locality wins out, and that depends on the pattern of the memory accesses and the computations that you're doing. So in general, you cannot say that one of these is better than the other. But the structure arrays is going to favor vectorization, because your loops will typically be over contiguous array elements. But it kind of screws your OO design to some extent. Okay, there is a nasty intermediate solution. Okay, so you can do if you're concerned about the vectorization, you can do something which is do array of structure arrays, okay, where the innermost arrays are short and matched to your vector length. Okay, so you could say, okay, I'm going to have a structure which represents 4 particles if my vector length is 4. Okay, and then so I have a structure which stores the data for 4 particles in arrays of length 4. Okay, so this should be this is a compromise, because it should be vector friendly, but not screwing your temporal locality too badly. Downside is, yeah, it's horrible. Okay, from a design perspective, it's just nasty. Okay, it's just doesn't make any sense from a sort of software engineering point of view. So objects, okay. So in terms of the data layout, there's pretty much the same issues as you have for structures. Okay. But with if we're doing OO design, the idea is that objects should be opaque. Okay, you shouldn't make direct accesses to the internal data, and we can actually use the language to prevent that. Okay, as it's often done. So you have you make your internal data structures in an object private, so that they cannot be directly accessed from outside code, from code outside the class. And that is, used, and that's usually implemented with special access functions. So you usually have, getter and setter methods for all your internal data to avoid exposing the actual internals. So that's, it's nice from a software engineering point of view because it means you can change the underlying data structure more easily because you are restricting the visibility of that to a much smaller fraction of the program. Okay, so only stuff inside the class cares about the actual internal structure, and everything else in the program that uses it accesses everything via methods, and doesn't have to know about the data layout. However, the access functions do introduce additional overhead, so both in terms of function calls and potentially also in terms of memory copies as well. Okay, because when you are rather than you're often returning you're returning the value of the thing and not its you're getting a copy of the value rather than the thing itself. So this is a problem only for only if you have small objects which which don't contain very much. And where the getter and setter methods just pick out a scalar or something like that, but it can be a serious problem, and you might have to work quite hard in some cases to make sure that your accessor functions are all inlined by the compiler. If they're not, then you can really suffer. Okay, other data structures, trees and lists and so on. So these are basically where we have structures or objects which contain pointers to other structures. And then you can construct arbitrary data structures. So this is, it's obviously it's a nice flexible convenience, but it has, this is basically, it makes the problems even worse, like slight pointer arrays, but even worse. So you have typically have a lot of memory accesses to navigate the data, and you've got some additional storage to store your pointers, and the access pattern is memory access pattern tends to be all over the place. A lot of modern languages have built-in support for these kind of things, so particularly C++, you have the whole STL full of convenient data structures that you can use in a library. So they have the same advantages and disadvantages, except that they're probably better tested and optimized. And the thing you have to be careful about if you're using libraries like this is that they are often optimized for some use cases and not for others. So you might be, your data structures may be, highly optimized for adding to the end of them, but inserting in the middle is slow. Okay, or traversing them is quick, but but extending them is slow. So it's not always. The problem is with using libraries to handle your data structures is that you don't really know directly, or you cannot see directly what the cost is of different operations, and it then makes it's impossible to optimize it. But you might make you often have some choices. Okay, so you might choose your data structure carefully depending on your common use cases for it. If you're building lists, are they lists that are going to grow and shrink a lot, or are they lists which you're going to allocate once and they stay the same size for the entire duration of the program? So you might want to choose different implementations depending on your common use cases. Okay, what things can go wrong with memory access? Okay, well, poor cache use. Okay, so that's either bad spatial locality or bad temporal locality. We can end up with unnecessary memory accesses, pointer chasing or temporary arrays, and aliasing problems. Okay, so using pointers can prevent the compiler from doing optimization. Well, what sort of things we can do about it? Okay, so yeah, just try to reduce the number of memory accesses. Things to look for, unnecessary pointer chasing, so pointer arrays that don't need to be pointer arrays, lists that could be arrays, unnecessary temporaries. And so if you can, on the other hand, but there are trade-offs. We have seen cases where introducing temporaries can help your vectorization. So again, this kind of idea can cut both ways, and things that would be cheap to recalculate. So this is an interesting one. Okay, so it's you often in so many cases you have a choice. If I'm going to calculate something more than once, should I calculate it once and store it, or calculate it again? And on modern processors, this trade-off is perhaps less obvious than you think. You'd normally think, well, okay, unless it's extraordinarily cheap thing, then it's probably better to calculate it once and store it. But actually, the cost of accessing memory, if your tables of values, if these things are large, and you've got random or unpredictable accesses into them, or they're big and they don't fit in the cache, and every time you access them, you're going to be consuming memory bandwidth, then it may indeed be better to recalculate. And if you're making this sort of trade-off, then particularly in the context of parallel codes, then you need to be testing in the regime where you're going to run. Okay, because if you do your trade-off testing on sequential code, then you can get completely the wrong answer, if you like, because of this idea. If you're just running a single process or a single thread to do your testing, then you're going to get access to more cache memory and more memory bandwidth and so the trade-off may seem not to benefit for a single thread. But then when your realistic use case is in fact an MPI program where all your MPI processes are doing exactly the same thing at the same time, so your level 3 cache capacity is reduced, and as we've seen particularly on the AMD REM chips, your memory bandwidth per core is massively reduced if you are once all your cores are busy, compared to just running a single thread or single process. So if you're doing this kind of testing or optimization, then you really need to be testing it in in the parallel context, where you are competing for your hardware resources, rather than testing in a sequential context. Sometimes that's relatively easy to arrange. If you're just if you're writing a piece of test code, then you can just simply put put an MPI, a trivial little MPI harness around it, just put just put MPI init at the beginning and MPI finalize at the end, and a couple of barriers in there, and that's all you need. So just to replicate the computation across multiple MPI processes. So they don't need to communicate with each other. You just want them to be doing all the same thing when you're testing these kind of optimizations. Okay, cache usage. Yeah, spatial locality. We want to use all of the data on a cache line as much as possible. So yeah, maybe structures are good, maybe they're not. But particularly looping over the fastest over the corresponding index of the array. Put variables that are used together close together, and avoid having gaps in structures if you can. Okay, so it's the idea of cache blocking. Okay, so what this is in terms of, if you think of it in terms of compiler optimizations, so there's a combination of what's called strip mining, so loop blocking or loop tiling, and also loop interchange. Okay, so that's swapping the order of loops in a nest. So this is designed to increase your data reuse. Okay, so we get both good temporal and spatial. Try and get both good temporal and spatial reuse. So for a given, there's a lot of choices. You're faced with a lot of choices. For a given loop nest, which loops are you going to block, and what's the best block size? Okay, so you can think about analysis can think about what's going to be better. So how big is your cache? I think you should say L2 is 512K on AMD rep, not L1. But so how many cache lines can you hold? Okay, so how many cache lines does each loop iteration take? So how many loop iterations does it? How many loop iterations will access enough data to fill the cache? So you can do some calculations, but in the end, you may just end up doing some trial and error. Okay, so the basic sort of idea of blocking transformations is basically loop tiling. Okay. So and the idea is that if you have a loop nest like this, okay, so this is so it's the one kind of like the good case where we had before. We've got a double nested loop which is accessing array indices. Okay, except that we've got a problem here because we're basically doing a transpose. So we don't know. So one of these is in this case, J is the right way around, but B is the wrong way around. Okay, so if we think about the array layout, so we're going J first. So I'm going to draw J across the way and I down. Okay, so it's a choice. Okay, I get upset when people start talking about row order and column order because that's really meaningless. You can choose whatever you like to mean for a row or a column to mean. It's just a convention that's inherited from matrix algebra. So it depends whether in most cases arrays don't represent matrices. So rows and columns just doesn't make any sense. Anyway, enough of that. Okay, so we've got J. So J goes across. So our memory access order, our loop iteration order goes across this way. Okay, so we go J first, then we go to the next value of I and go across like that. Okay, so we're scanning across. Okay, so the idea of loop blocking, okay, is to break this up into little blocks and then iterate across the little blocks. Okay, so what we're going to do is introduce two extra loops here. Okay, so we have an outer II loop, which is going to do the I blocks, a JJ loop, which is going to do the J blocks, and then so these have strides of length b, which is the block size, and then we have our inner loops over. So the inner I and j loops just operate within each block. Okay, so that's the idea. Okay, so the idea is that we are basically we can reuse the data, hopefully inside this block. What gets loaded in the cache here, we get to reuse data as much as possible before we move on to the next block. Okay. This can also be helpful for vectorization. Okay, so in a case like this where we have so aij depends on j minus the j-1 and j+1 values here, and we're looping over innermost loop is over j. Well, in that case, our j loop won't vectorize because of the dependencies. But we could block the in this case we could block the I loop, okay, and then move the I loop innermost, and do the also potentially do the index swapping. Okay, so now our inner loop is basically inner loop is over I, and I is contiguous, and also the I iterations are independent, so that will vectorize. So the same kind of ideas can be used for blocking. So also mentioned it in the context of the previous lecture. One of those examples at the end, where we wanted to split the loop so that and introduce some array temporaries in order to keep your array temporaries sufficiently small to fit in the cache. You might want to do blocking. So that's basically the same. It's the same idea. What you can do, okay, so basically perhaps if you have if you have multiple successive loop nests, then and you're iterating over large arrays, then essentially what's likely to happen is that by the time you get to the second loop, then the first elements of the array will have gone out of it, would have been evicted from the cache before you get there. Okay. So what can you do? Well, you can think about fusing your loop nests. Okay, so as long as the iteration spaces match sufficiently well, you can put it all into one loop nest. So you can either do it completely, or you can do partial fusing. So downside is that if you do this too aggressively, you can end up with very large loop bodies. You can eventually run out of registers. Not too big a problem on modern hardware. Register files are large, so but ultimately you can. Okay, if you end up with loop bodies with an awful lot of temporary variables in them, then you can run out. Okay, so the idea here is something like this. Okay, so our original code has 2 loop nests. Okay, so complete fusion would be, okay, let's just move this, the iteration spaces match and there aren't any dependencies, so I can just merge them together into one. Okay, so in that case, both, hopefully the accesses to aij in the second statement, these are all going to be cache hits because I've already loaded aij for the previous statement. Whereas in the original case, it might not be. If the arrays are big enough, then by the time I get to this to do this loop, then A11 may have already been evicted from the cache and so on. So I might have to load it again. Okay. So you don't have to go the whole hog. You can do the partial thing. Okay, so you can just you can fuse the outer loop but keep separate inner ones. And again, so provided you're provided one of the dimension, one dimension of your array still fits in the cache, then you're still getting good reuse, but you're not increasing the size of the loop body. So other things you could do, well, perhaps you want to do your cache blocking first. What happens if you have, if you need to if your reuse crosses subprogram boundaries, okay, then you might want to remove your outer loops, move outer loops out of your functions. Okay, so haul your outer loop into a parent routine, and make the loop make the function just operate on one iteration of the outer loop. Okay, so good for things like OpenMP. So you're basically increasing the size of the amount of work in the loop. Okay. Okay. Array syntax. Okay. So what I said about array syntax before is true up to a point, maybe, but I'm not sure this is really true. Okay. I think compilers are maybe better at doing this than they used to be. Okay, but you might worry about that the compiler doesn't do any loop fusion for you in this case. But yeah. Okay, yeah. So this is your idea here. Okay, so it's basically you'd have so calling two subroutines. Then you basically say, okay, I'm going to say and they both got a loop inside them. You pull the loop outside and you pass the loop index in. Prefetching, okay, so most modern processors will do automatic prefetching. So this is the process by which the hardware, the memory system tries to anticipate what data you're going to use next and preload it into the cache for you. So regular access patterns are recognized, and then the cache lines will actually be fetched before there's any actual load or store issued for those lines. It usually only works for contiguous sequences of cache misses. Okay, so the lines that are if the lines being loaded are contiguous in memory, then it'll start fetching the subsequent ones. So these days, most previous processors, they only did it forwards. Okay, so but modern processors tend to work if you're accessing linearly in memory, but backwards. So that tends to work okay. The processor basically has a set of buffers, and where each holds the address of an active prefetching stream, and so if you're loads the current block, cause the next one to be prefetched, and the stream address to be updated, and so on. Okay, and so a stream is initiated or established by a sequence of cache misses to consecutive locations. So if you get maybe 2 or 3 consecutive cache misses in a row, it will then establish a stream and start prefetching the subsequent blocks of memory. Okay, so how to use these? Well, this will work well if you again use linear access patterns. Okay, so if you're going linearly through memory, this is another reason why you should prefer that memory access pattern. Is that it will trigger prefetching. Okay, so actually only the order of cache block accesses need to be linear. It doesn't have to be linear access to every word. It just has to be linear access to blocks. But it's most likely to be, the most easy thing to do is, or the most common case is probably have linear access to the array words anyway. Okay, so most loops will require multiple streams because either because you're accessing different arrays or you're accessing different parts, different distinct parts of the same array. So eventually, if you have a loop with a lot of different array accesses in it, then you can run out of streams. Okay, so in which case it's maybe possible, it's maybe better to split the loop so that the number of array accesses doesn't get too big. Yeah, and prefetching normally stops when you get to an operating system page boundary. So that's a reason for a possible reason for using huge pages, though in practice I'm not sure it really helps a lot. Okay, and some details about how to use huge pages on Cray systems. Yeah, it's possible to do. Okay, it might make a difference in some cases. I won't discuss it in detail. Okay, what else? Pointers. Yeah. Okay, so pointers are useful, but typically bad for compiler optimization. The problem is that compilers try very hard to reduce the number of memory accesses. So only loading data from memory once and keeping a variable in a register as long as possible, and only storing stuff back to memory when it needs to. So problem is that if you do wild things through pointers, the pointer could point anywhere. So in order to be safe, the compiler will reload everything after a write through a pointer. Okay, so it has to assume that when you write to the address of an arbitrary pointer, that could have updated anything that was currently stored in a register. So it has to throw out all the contents of the registers away and reload everything. Okay, and it also has to synchronize in memory, okay, before a read through pointers as well. So pointer-based, sort of unrestricted pointer-based accesses are generally a bad thing for performance. Okay, Fortran. Okay, so old style Fortran didn't have any pointers, but you still do have arguments passed by reference. Okay, so basically when you're passing variables into subroutines in Fortran, you're actually passing the address. So subroutine of arguments effectively the same as pointers in this respect. Okay, but okay, it's illegal Fortran if two of your arguments overlap. You're not allowed to have two arguments to a subroutine to reference the same memory address. That's basically, so the compiler will assume that you're not doing that because it's illegal. Okay, so that's why Fortran can avoid that problem. It just bans it in the language. Okay, so more modern Fortran does have pointers, but they're restricted. They can only point at things declared as a target. Or a target to another pointer. So the compiler therefore knows more about possible aliasing problems. Fortran pointers can't just point anywhere. But nevertheless, it's probably better to avoid them for performance critical data structures. So you don't want to be using, you don't want to be accessing through Fortran 90 pointers in your innermost loops, in your performance critical bits of your program. C, okay, well, C pointers are basically unrestricted, so you can get some really bad performance problems. So what can you do? Essentially tell the compiler that you're not doing anything bad, okay? So use the restrict keyword, which I've already mentioned where you can, okay? Or you can also do it via compiler flags as well, okay? You can tell the compiler that you're not doing anything bad, okay? You can also improve stuff by using scalar temporaries inside your performance critical loops. So have a scalar temporary, dereference the pointer, and store the value in the temporary. Use the temporary variable inside the loop, and then the compiler knows what it's doing. It knows you're not doing anything. It knows you're not doing anything crazy with your pointers. Okay, and that is it. Anybody have any more questions? So Andrew asking, does loop blocking have to be done in programming, or can compilers be asked to do it? So answer is, simple cases, you may be able to persuade the compiler to do it. So that would be through compiler directives, potentially. And I don't think it's widely implemented yet, but the latest versions of the OpenMP standard have loop transformation directives in there. So that will hopefully become a portable way of asking for that kind of thing. But so compilers can potentially deal with simple cases, but anything that's remotely messy, so like non-perfectly nested loops and things like that, you may be out of luck. Okay. So probably you have to do it by hand. Okay, so Andrew's asking, the compilers risky pointers could be referencing data outside the cache, causing a reloading in the cache. It's not really a problem with the caches, because so the whole memory system, including the caches, is completely transparent to what's going on in the processor in some sense. It's more to do with what's stored in registers. Okay, so that's the storage inside the core, where the instructions get their arguments from and write their results to. Okay, so when you load data from memory, it will go into a register, and then the registers will feed the floating point operations, for example, will take their operands from the registers. So when the compiler tries to optimize, it tries to store things, keep things in registers as much as possible, and avoid loading and storing them from memory. But it has to then, the compiler has to then take care of this. So what happens if the value in memory could potentially change, then a value stored in a register could go out of date. So that's essentially what it has to protect against. So if you just write through a pointer, it could, that pointer could potentially point to any of the storage that's currently got a copy in a register, and therefore it'll have to reload the data from. So yeah, it's more a problem with register storage rather than cache storage. There's pointer references data outside the cache. That's fine. Okay, that'll just it will cause, it may cause a cache miss, but it's not it's not a problem that the compiler can deal with. Okay, so that's the last of the talk material for the course. So I will be around for the next hour or so until 4:30. If anybody wants to ask any questions, wants to do anything more with the practical exercises, please feel free to do so. Otherwise, now would be a great time to fill in the feedback form for the course. So that's the direct link to it there. That would be great. Very helpful. If you we're always grateful for any feedback that we get. Help us improve the course for subsequent runs, and also to let us know what other topics you might be interested in. Yeah, and also if you've got questions that are specific to a particular application that you're working on, I'm very happy to try and help you with that. Try and answer questions if you've got questions about a particular piece of code or something like that. Yeah, I'll be around for the next hour. But otherwise, please don't feel free to hang around to the end if you need to get away. Appreciate it. It's 3:30 on a Friday afternoon, so I'm sure some of you will have better places to be than hanging around on here. Otherwise, thank you very much for listening.